So, Nahi asked some nice questions last time that I've been thinking about, so I'll try to answer those today as well. So let's start with the classical limits of the Bose-Einstein and the Fermi-Dirac statistics, right? Actually, we are going to look, yeah. So what is the Bose-Einstein statistics? The Bose-Einstein statistics says that the density of states at energy E is given by, for non-interacting particles, 1 over exponential, beta is the inverse temperature, E minus mu plus, minus 1. Now, this, we'll talk about the limit of this, but, right now, like what happens with the singularity. But for right now, let's concentrate on something else. So this is the Bose-Einstein statistic, and then there is the Fermi-Dirac statistics. Okay, somebody's microphone is on. They're probably eating, so probably want to turn that off. Thank you. Otherwise, Ramjan Mashe eating is.
I wasn't eating. It's just background static.
It's all right. I drink coffee while I'm running my class all the time. All right. So Fermi-Dirac statistics is just a different. It's just this. Okay. So now, if you look at the limit in which beta E minus mu is much, much greater than 1, then we can ignore this factor of this term minus 1 and plus 1, right? And in that limit, both of these statistics, so this is Bose-Einstein, this is Fermi-Dirac. It should be Dirac-Fermi, but I guess Dirac is the one who named these things, so being a modest person, he put his name at the end. So in that limit, what happens is that both of them become Maxwell-Boltzmann statistics, okay? And the way to understand this is that, when does this happen? This happens when, mu is much smaller than E, right? And when mu is smaller, is very small or even negative, it means that we have very small density. For example, remember that for the ideal gas, we computed mu as kBT log of lambda q n over v, right? So mu is actually small or negative when when the density is very, very low. So what it's saying is that in that limit, there are many more thermally allowed states than there are particles, and thus the restrictions placed on those particles due to, say, quantum statistics or symmetry of its wave function, they are not very relevant. So particles can behave more or less classically, okay? So, in So in the limit, okay, so that's one thing. So the other thing.
Could you elaborate upon the last phrase, statistics or occupation number and symmetry are not a major factor?
Right. So suppose that you have like a thermally allowed state that is, say, some. So if we are considering, say, a bunch of particles in a box, right? So when we have a particle in a box, there are its momentum modes are quantized, right? And there are, say, a lot of momentum modes, and the number of particles are few. And suppose that we are looking at fermions. Okay, so we have a box, and we have a low density of particles, and it's very unlikely that a given momentum mode is going to be occupied by more than one particles, right? So if they're fermions, of course, they cannot be occupied by more than one particles, right? But if all the states were occupied, say all the states were occupied, if there was a lot of particles such that most of the states were occupied, right? Then if you have another extra particle and you want to accommodate it, you would have to take into account that all these states are occupied, right? And then basically the quantum nature, the occupation number restriction of the fermion will come into place, right? Another thing is the symmetry. Symmetry of the wave function means that bosons have a natural affinity towards each other because they're attracted, because they're symmetric. And fermions have a natural affinity, like a repulsion, because they are antisymmetric wave function. And and if you have lots of particles, then again, if you have lots of particles, then if you want to squeeze two fermions together, the fact that they're fermions is going to start playing a role, and there will be an effective repulsion between them. And if there are bosons, then there will be, the fact that they can actually be in the same state without any energy cost means that there will be effectively some sort of attraction between them. And those things, will play a role when the density of the particle is high. And what I'm saying is that because the density of the particle is not very high, all that matters is that these factors that I just talked about is not going to be they are not going to be important. Okay.